Hello everyone, welcome back to awesomehelp.com, oscmhelp.com. Today we are going to take a look at a problem pertaining to uh, line weighting management. It's actually a fun one here, and what we're going to recognize is we've already worked on looking at how to determine which line weighting model we're going to use, whether that's the MM1 model, which is random arrival rates, random service rates with one server in the system. We're going to look at whether this is an MD1 model, random arrival constant service time, one server, or whether it's an MMS model, random arrival, random service, and multiple servers. So let's go ahead and take a look at the problem here. Vending machines operated by PepsiCo at various sites break down periodically and require maintenance. A vending machine does not generate any profits for the company when broken down. Makes sense. PepsiCo has calculated that its vending machines break down at a rate of 3 per hour on average. So if we put this little sentence here, PepsiCo recognized that its vending machines break down at a rate of 3 per hour on average. Average tells us that we're looking at random. Random what? Random arrival, random service. Looks like machines are breaking down at a rate of 3, or 3 broken down machines arriving to the company per hour on average. So just talking about the model system, that right there describes random arrival. And we know in this case that the arrival, also our lambda symbol, arrival rate is going to be 3. Let's continue reading. Each vending machine generates $500 of profit for the company per hour, and the time to repair a machine varies. One service technician can service the machines at a rate of 5 per hour. 2 service technicians working together can service the machines at a rate of 7 per hour. 3 service technicians working together can service the machines at a rate of 8 per hour. So by just looking at the problem first glance here, service time appears to vary, and not only does it appear to vary, but it's going to vary determine on the number of workers. So far we have random arrival of broken down machines, 3 per hour. Random service time, that's our service rate per hour. Looks like it could be 5, 7, and 8, but if we continue reading, it's going to tell us that how much the technicians are paid, $40 per hour. And then there's some very key information here. No more than 1 crew can be deployed due to tool shortages. So if you're working through this problem, you're thinking to yourself, there's multiple service techs, meaning that it's got to be an MMS model, multiple servers. The reason why that would be incorrect in this situation is because we can read here no more than 1 crew. 1 crew is the limit, meaning 1 server. But the main question we're trying to solve, what is the best or ideal crew size? We know that when we have 1 worker that we're looking at, that's just notating there that we have a service rate for 1 worker, 5 can be taken care of per hour. When we have 2 workers, our service rate changes to 7. And if we have 3 workers on the crew, our service rate jumps up to 8. So we want to determine the ideal crew size. The very next step we want to take a look at is what's the minimum number of crew possible to even make this system work. If you recall a little earlier in the section, we look at system utilization, which is written in the notation of P equals your arrival rate over number of servers times the service rate. This here must be less than 1 in order for a system to function. If the utilization is greater than 1, then what that tells us is that the system will break down. So just by looking at what we've got here, lambda over mu, or arrival rate of the broken down machines over the number of service repairs per worker, we're going to solve for the utilization rates to see where we should start with this problem. If we do the utilization rate of 3 over 5 and 3 over 7 and 3 over 8, that will tell us the utilization for each one. 3 over 5 is going to be 60% or 0.6. 3 over 7 is going to be 0.428. 6. You can round however you want, and 3 divided by 8 is going to give us 0.375. So just by looking at whether 1 worker, 2 worker, or 3 workers is even feasible is already determined in the first calculation. System utilization rate of 1, we have 0.6. It's operating, it's less than 1, meaning that we can start with 1 worker. So we're going to want to make a table actually for this problem. You may have already done this a little bit in class, but the table is going to basically help us determine the total costs. That was ugly. I'm going to try to fix this real quick. We want to determine the cost because it's a business and we want to make as much profit possible and minimize costs. So we're going to look at 1, 2, and 3 crew members. But remember that at all times this is only 1 server or 1 crew, but the crew size can be 1, 2, or 3 service techs. We know that the cost per crew member, $40 per member per hour will be necessary. If we have a crew size of 1 member, we're looking at $40 because $40 times 1, $40 per hour times 2 is going to give us $80 per hour for this crew, and crew size 3 would be $120 because $40 per hour times 3 workers. So with trying to determine the next step, we saw in the problem that each vending machine generates $500 of profit for the company per hour. If we have machines that are breaking down or are now out of service, we're losing the company profit. For every machine broken down, we're losing that $500 per hour. But we're going to try to calculate the next section, which is LS. And for your reference, I know that there are a lot of these symbols. LS equals the average number of, in this case, machines in the system. We're going to go with in the system because if we are looking at, we're trying to look at the total time that the machine is out of service. Total time machine out of service. The total time that a machine is going to be out of service is from the time that it breaks down all the way until the time that a worker is going to begin serving, servicing, which means that the wait time, sorry for my bad handwriting, wait time plus service time equals the total, time or the total number of machines in the system. And so in order to solve for LS, we need to find the formula here, which is going to be LQ, can be found on the oscmhelp.com under line waiting management. There's going to be a legend of formulas as well as the symbols and legend. So hopefully that will help you, but that's where I'm getting this from. LS equals LQ plus arrival rate over service rate. And we've already solved what this is, the arrival rate over the service rate for each one, which is right up here when we have crew size of 1, crew size of 2, and crew size of 3. So we're already able to know part of that problem. But now we need to find what LQ is, and in order to solve for LQ, that's dependent on the type of model that we're working in. So I'm going to give us a little bit more room here. I don't think we'll need to read any more of the problem at this time. LQ in an MM1 model is equal to arrival rate squared over service rate times the arrival rate minus service rate. Again, this can be found in the table and formulas provided under line waiting management. And so just for clarity's sake, LQ with our one worker is going to be 5. So we are going to do 3 squared over 5, 3 minus 5. Let's go ahead and calculate that out. I know we're going to have 9 on the top, and 3 minus 5 is -2 times 5, 10. I think I might have just done a little backwards calculation. Sorry, you will notice that I made an error. It's going to be backwards here. I'm going to erase this. For those of you watching, if you caught it, great. You already know the material. You're doing a good job. Keep it up. If you didn't, this is just a good note that you got to be very careful with your notation. It happens. There's a lot of variables at play. No harm, no foul, though. Just small arithmetic. We can fix that. So now we're going to have a positive 10, which equals 0.9. LQ for one crew size is going to be 0.9. And we're going to do this exact same thing for 2 workers, or 2 service techs. 3 squared over, now the service rate, if you recall, up from the top here, is going to be 7 per hour. 2 workers working in the same crew can service 7 machines per hour. 7 minus 3. Now looking at 9 over 28, if I'm not mistaken. 9 divided by 28 is going to give us 0.3214. Sorry that we're running out of space here. And we're going to solve the last one now. LQ with 3 workers. Still have 3 machines breaking down per hour. Now we have a service rate of 8 per hour. 5 times 8, we're looking at 40 on the bottom, right? 9 over 40 is going to give us 0.225. Cool. So we just found very important pieces of information for solving LS, which again, just coming back up here, LS equals LQ plus the arrival rate over service rate. So I'm going to actually write out the formula here for you. Hopefully make it a little bit easier. 3214 0.225 plus, we have, if we scroll back up, 0.6 for this portion of the problem, arrival rate over service rate for 1 worker is 0.6. For this one's 0.42, let's go with 9, and plus 0.375. So now we're going to calculate the total to get our real LS value for each of these. At 1.5, we have 0.429 plus 0.3214 gives us 0.7504. That's a 7 for those watching. 0.375 plus 0.225, 0.6. Now, we want to determine, this is kind of the biggest trick of the whole problem. If we're losing $500 per hour for every hour that one machine is broken down and out of service, we need to recognize that LS is the average number of machines that are in the system every hour. So when we have a crew size of 1 member, there is 1.5 machines on average in the system. When we have a crew size of 2, we have a machine in the system for 3/4 of an hour, and for 3 crew size members, 0.6 hours. So that's why we're going to multiply $500 per hour times 1.5 machines per hour, and 500 times 0.7504, and 500 times 0.6. This is going to give us the total cost for the machines themselves. Sorry, I have to erase this so I have a little more room to write the totals. Thank you guys for your patience. Let's go ahead and solve for what those are. 1.5 times 500 is $750. 0.7504 times 500 is going to give us $375.20. And the last one, 0.6 times 500, is going to give us $300. And I'm going to write this as cost of machines in system. And finally, PepsiCo wants to know the number of crews or service techs necessary to basically minimize the cost. So the total cost here, $750 for the machines being down and out of service, plus $40 per the labor for the crew, giving us $790. Then I'm going to do the same exact thing across the board. $375.20 plus 80 gives us $455.20, which means that already two service techs working together is going to be better than one. And let's see if that holds true for the last one. 300 plus 120, $420. Excellent. In this problem, a crew size of 3 appears to be the best at this point. I'm assuming that it's probably going to be the correct final answer. The reason why I say assume is because we see a trend that every time we add a crew size member, the cost is going down, which would mean we probably want to take a look at what it would be with 4 crew size members too. It could be cheaper. I'll go ahead and let you figure that out for the last one, and I'll put in the notes section what that final answer is. But thank you very much for watching this. If you have any questions, concerns, please feel free to leave a comment. Thank you for visiting awesomehelp.com.